Why is microscopic buckling crucial for composite design? Imagine tiny fibers inside a material suddenly bending under pressure, causing the whole structure to weaken. That's what microscopic buckling is all about. It's a small-scale failure that can lead to big problems in composite materials. When fibers buckle at the microscopic level, they can start a chain reaction that results in cracks, kinks, or even complete collapse of the part. This is why understanding this failure mode is so important for designing strong, reliable composites. In fiber-reinforced composites, fibers are held together by a matrix, which is usually a type of plastic or resin. When you push these composites in compression, the fibers bear most of the load. If the fibers are not perfectly aligned or have tiny imperfections, they can buckle under pressure. This buckling happens at a very small scale, often just a few micrometers wide. To give you an idea, a micrometer is 1/1000th of a millimeter. It might sound tiny, but it has a huge impact on how the entire material performs. There are two main ways fibers can buckle microscopically. One is called in-phase buckling, where fibers deform together in a wave-like pattern, supported by the surrounding matrix. The other is out-of-phase buckling, where fibers bend individually, causing localized damage. Both modes affect how the composite reacts to loads and can trigger larger failures if not properly managed. Several factors influence how easily fibers buckle. Small imperfections in fiber alignment or waviness make buckling more likely. The stiffness and strength of the matrix material also play a role because they support the fibers laterally. How densely the fibers are packed and their arrangement within the composite influence the buckling threshold. For example, square or hexagonal fiber layouts change how fibers support each other under compression. Additionally, in layered composites, the constraints from neighboring layers can alter how fibers deform and buckle. Designing against microscopic buckling involves choosing the right fiber orientation, selecting a supportive matrix, and arranging fibers carefully. By doing this, engineers can increase the load a composite can handle before fibers buckle. This approach helps prevent early failure and extends the life of the product. For example, in aerospace or automotive parts, avoiding fiber buckling means safer, more durable structures that perform well under stress. Understanding microscopic buckling also guides testing and computer modeling. Engineers can simulate how tiny imperfections might grow into larger failures, helping them improve designs before manufacturing. This detailed knowledge allows for better prediction of failure modes and more reliable materials. In the end, microscopic buckling shows us that tiny flaws or deformations at the fiber level can escalate into major problems. Paying attention to these small details in design and material choice makes a big difference in preventing catastrophic failure. It's a reminder that in composite engineering, the smallest elements can have the biggest impact on safety and performance.